Hello, everybody. So now we come to chapter 3. Now, in the past, maybe at the beginning of chapter 2, I mentioned that calculus can be classified into two subfields. One was called differentiation or differential calculus, and the other being integrals or integral calculus or integration. So now we go into the first of those two as we define what a derivative is at a certain point, and that's section 3.1. So let's get started as we study or jump into the study of derivatives. Before we go into chapter 3, take a look at these two men. One on the left is Isaac Newton, Sir Isaac Newton of England, and the one on the right is Leibniz. These are the two men who are credited with beginning or starting calculus back in the actually 1600s, and so the 17th century. And what do you think? I think the first thing you may notice is their hair. Like, what's up with their hair? Like, do you have to have long hair to study calculus? But anyway, they, as you know, they made this remarkable accomplishment, which is, to study or to introduce to the world the important concept of calculus, and that really brought the different school of thought into philosophy, which says that science can basically rule the world. We can study motion, the things infinitesimally small and something very large, both by studying their mathematical underlying relationships, which can be described by this idea, the new idea called calculus. So that's amazing. Okay, and just one little thought about Isaac Newton. So Isaac Newton was a young student in England, the university, back in 1666 when a big epidemic began and all the schools shut down. So he had to go home to his rural house where he grew up outside of London. And then the year in 1666, because he couldn't take classes, he basically sat down and thought, and then decided to write some of his thoughts. And out from that year of thinking came three books, one on optics, another on the universal gravitational force, and a third one on calculus. What's the point here? Well, let's remember that out of these things like epidemics and pandemics, sometimes good things can come out. So don't write off these years of pandemics yet. Okay, so now let's get into section 3.1. All right, so we start with this picture. Now, this picture is something that you should be familiar with, something like this, because I have drawn this many times. All right, so let's say we have the function, which we can call f, and f has, we have 2 points on that. One is at a, which is a comma f a, of course, and the other one we'll just call this generically x. And of course, the value of the function right here is fx, right? The first thing I want to mention is the idea of the tangent line. Now, what you are seeing here, the blue line is not tangent line, obviously, right? We want to find, see, as I mentioned back in chapter 2, the idea of the derivative has to do with the slope of this line. We want to find not the blue line, the tangent line. We want to find its slope, the slope of the tangent line. Okay, the question is how do you do that? Because we don't have a tangent line at the beginning, we'll have to start with some other line, and that's the one that I'm showing you. So pick x. Okay, so first pick x, as you see here. All right, and then you draw this line. Okay, now this line is called the secant line. basically what a secant line is a line that connects 2 points on the graph, okay? And so that's exactly what you see here in blue. Pick X as seen, and or maybe as I guess I should say as shown, and draw the secant line. Now the secant line goes through A and X, right? Now the M secant line, this is the slope. I guess I should say M with a SEC as the subscript. M secant, this is the slope of the secant line. And as you know, this is as defined, it's the rise over run, and that is delta Y over delta X. Otherwise, you can also write this as f of x minus of f of a. That would be the difference between these two values, two y values, divided by x minus a, which is the distance between a and x below, right? Now, this is actually also called the average rate of change. Average rate of change between these 2 points, or on this interval from a to x. Right? So if you are asked to find the average rate of change, all you have to do is to find the slope of the secant line. All right, so this is one picture. Now I'm going to draw another picture here in a moment. So give me just a moment and I will be right back. Okay, so when I say I'll be right back, of course, I'm pausing the recording. And from your standpoint, you're not going to see any lapse of time. But what I have just drawn is a similar picture. I'm going to identify some of these points slightly differently. I'm still going to call the point I'm interested in the x value of a. And of course, this is the origin. And so this y value will be not f of x, but what? F of a. And then here is another point. And then this time I'm going to describe the difference between, a and what I used to call x, h, right? So this distance is called h. So this point, the point I used to call x, can just be described as a plus h, okay? So h stands for the difference in the x coordinates. And then this here would be f of a plus h, not surprisingly, right? That's the y value. And so the difference, of course, is delta y. And of course, this delta x is actually h, right? So with this setting, which is often used in defining the derivative, we are going to let h be equal to x minus a, right? And you should, get used to this because many people use this notation, and we too will be using this notation. All right, in this setting, an average rate of change, which is the slope of the secant line, okay, still delta y over delta x, but now it's going to look slightly differently. F of a plus h minus f of a, that would be the difference between those two y values, divided by, now this time it'll be just h in the denominator, right? And this is also called the average, well, the average rate of change, of course. But this one in particular is called, actually the top one too, these are the same thing, but this has a name. It's called the difference quotient. Because these are interchangeably used, both of these can be called the average rate of change and the difference quotient on this interval, a from a to a plus h. Okay, now comes an important part. And this is really what distinguished calculus from any kind of previous mathematics. Now we let h go to 0, infinitesimally small and closer to 0. Okay, so those three words I have been using repeatedly, closer and closer. Okay, those three words almost define the most important characteristic of calculus, right? Which is to get things, smaller and smaller until it approaches 0, but never gets exactly to 0. All right. In fact, there's a famous book on real analysis, which includes the foundations of calculus. And the title of that book is Closer and Closer. How beautiful is that? Okay, all right. So now, as you do this, the secant line becomes the tangent line as you do so, all right? And as you take the limit. So here's what I'm talking about. Let's say if I can use my colors. So blue line. Okay, so this was the secant line, right? If you pick another point, let's say this point. Okay, so what am I saying? I am saying if you pick this point here, H is a little smaller. Okay, now you have a new secant line. And if you pick another point here, then you get another secant line. Let me explain what that is. So now here H is a little smaller and we have another secant line. If you continue to do this, this is secant line 1, 2, and 3. And if you let H go to 0, closer and closer to 0, infinitesimally close to 0, then eventually you get this blue line, which is going to basically touch the graph right at this point. And this is the point, the only point at which the line touches the graph. And this line, the green line, is called the tangent line. Tangent just basically, in this case, means it meets a curve at one single point. All right. So that, I think, is sort of easy to understand. And here's the definition that you should really take to heart, because now I'm going to define what the this whole section is about, which is the derivative. All right. So the instant rate of change, that derivative, this is the word I'm going to define. I'm defining the derivative of f at x is equal to a is this note, and the notation for the derivative at a is this: f prime. Now prime is because it has been derived from the original function f. So it's like a derivation, right? The derivative of f at a is equal to the difference quotient. Actually, let me go ahead and do it this way. You write the difference quotient, which is f of a plus h minus f of x. Oh, sorry, f of a all over h, which is, delta x, right? And so that itself is the slope of the secant line. And as h gets smaller and smaller, this becomes the slope of the tangent line. And so that process is the limit process, which we learned in chapter 2. So the limit as h approaches 0 of the difference quotient is what we call the derivative at the point. And I want to emphasize that this is the definition of the derivative at a single point. And because it's a limit, it's going to be a number. Okay, later on, we will talk about the derivative as a function. But at this point in section 1 of chapter 3, we are going to be just discussing the derivative at a single point. All right. Sometimes this limit doesn't exist. So we will make and add a disclaimer if it exists. If it does not exist, of course, it's not the derivative, right? Now, this is the slope of the tangent line, or I should say the slope of the line tangent to f at that point, okay? It's also the instantaneous, what do you think? Instantaneous rate of change of f. So this is how quickly f is changing right at that moment, all right? So this is like that number you read in the speedometer of your car at every single point. As you accelerate, your velocity function or speed function is, increasing, right? And as you accelerate, every single moment of time, your speed is actually changing, going from like 60 to 62 to 63 to 67, it's changing, right? And at every given moment, How do you even figure out how fast it's going? Well, because, well, I mean, your car is not doing calculus, but it's approximating, how quickly your car is moving. And so that whole idea, the instantaneous rate of change, is what that derivative is describing. Okay, it's also the slope of the tangent line. So both of these interpretations are going to be important. All right, so now let's try to find do a couple of examples, right? And this is the type of problems you are expected to complete for this section in your assignment. All right, so the first example, let's use an easy example, x squared, and let's try to find the slope of its tangent line at 3. So what are we talking about? All right, so you know your parabola, that's x squared. At 3, the value of the function is 9, okay, because it's x squared. Now, the tangent line is going to look something like this. So you can expect a pretty steep tangent line, meaning that the derivative, which is the slope of this tangent line, the instantaneous rate of change, should be a pretty big number, right? It's not going to be negative because it's increasing, and it's not going to be 1 or anything like that. Okay. Now, if I ask you this in 2 weeks, I think the answer, you can give me the answer like right away, like within a second. So what is the derivative of x squared at 3? And you'll say, oh, the answer is, okay, but not yet, because as of right now, this is the only thing we have, right? And so we are going to work out this limit. So what is that? All right, so here's, okay, I'm going to formally write what I did in the definition, because this is the first example. So it's f of, doesn't look good, f of 3 plus h minus f of 3 divided by h, and you take the limit of this. And unfortunately, just like we learned in chapter 2, because we are saying this is equal to, and this is still a limit, I have to write this lim as h goes to 0 on every single expression. All right, now what is 3 plus h? Well, that's just a value, but what is f of that? Well, f only squares its input, right? So this will be 3 plus h squared minus 3 squared, which is of course 9, divided by h. Now this doesn't look so bad. I mean, after all, we have just spent a lot of time studying chapter 2, right? So this is 9 plus 6h plus h squared minus 9. That's on the top. Remember, when you square a binomial, you get 3 terms, right? Okay, and then you can see, oh yeah, 9 and negative 9 cancel. And in fact, you can also see that 6h and h squared both include h, so you can factor out h. You see why that is important, right? Because you still have that h in the denominator, which needs to be canceled, and we have now found a way to cancel h, which is the bad guy, which is the thing that was preventing us from being able to substitute h is equal to 0. Now we have the limit of 6 plus h as h approaches 0, and of course that is 6. And that is the answer to this question. What is the rate of change of x squared at 3? The answer is 6. As we expected, this is a rather large slope, and it's a positive number clearly because the function is increasing at that point. All right, so that's how you can find this. It's not too bad. What happens if you have a function like x to the 15th? Well, then you would have to expand this to the 15th power, which will require like 16 coefficients, as you remember from the binomial theorem, and that seems to be very complicated. But don't worry, we will have nice formulas in the next section, and we will be able to figure those things out rather easily in the end. All right, another example. This time, let's say f of x is the inverse function or the reciprocal function. And let's try to find f prime of x at 2. Do you remember what the reciprocal function looks like? It's a 2-component function. It's the hyperbola. And of course, it's not defined at 0. 2 is going to be here. The value of the function, of course, is 1/2 because it's just a reciprocal. We are going to look for the slope of this tangent line. Now, it's going to be negative. You can see the slope is negative at that point, right? So you can sort of predict what kind of number you'll see. And it's not going to be like -15, all right? It's going to be somewhere between 0 and -1 because just the graph, it seems to indicate it's not a number that's going to be very far from 0. So let's go ahead and do this. Oh, by the way, I am going to tell you now what I have written here. Okay. Now, I have written this as a mathematician because the limit of this is equal to the limit of this, which is equal to the limit of this, which is equal to the limit of this. And, you know, of course, you get tired of writing LIM so many times, right? So even though officially in public, I would be writing this, if while I do that, and whereas I do this in public, if I were trying to find this on my own, I may actually use my shorthand notation. Let's see, use a different color for shorthand notation. I may just say, you know what, this will be like f of, well, okay, so I may just write something like 3 plus h square minus, 3 square over h. And that's going to be 6 plus, 9 plus 6h plus h square. Of course, I'm doing the same thing, minus 9 over h, and I'll cancel these, right? And I can see that this will be the same as 6 plus h. And now I can say this is equal to 6. Okay, see, this is bad, right? This is mathematically not right because I am not saying h is 0. In fact, I don't allow h to be exactly 0. So I don't want to write it this way. The equal sign is like a sacred symbol for mathematicians. So we don't want to abuse that. So what I will do is this approaches 6 as h approaches 0. So this is like a shorthand notation. This way, if you write it this way, I don't have to worry about, violating my the sacredness of the equal sign. And at the same time, I don't have to write LIM as h approaches 0 every single time. So this is one way to do that. Let me go ahead and use that shorthand notation because I don't want to write LIM every single time. All right, so here, okay, let's try to find this. What is that? It's going to be 1 over 2 plus h. Oh, maybe I should go ahead and start by what the definition looks like. F of 2 plus h, remember, minus f of 2 divided by h, okay? I'm going to eventually take the limit of this difference quotient as h approaches 0, but of course I have to somehow cancel that h. Okay, what is f of 2 plus h in this case? Well, it's a reciprocal function, so this is what you get. Ooh, this is a fraction inside of a fraction, or fractions inside of a fraction. This is called the rational expression, right? You may have learned about this in what, intermediate algebra or something. All right, so you have this h in the denominator. Let's try to figure out how to add these two fractions. Well, you need a common denominator. The common denominator in this case is this times 2, right? And of course, you have 2 on here. Maybe I'll just be more precise. 2 plus h times 2. And of course, here, what you need is 2 plus h. All right, all I'm doing here, and I hope you know how to do this, is this thing is exactly that, right? Because you just have 2 and 2, you can cancel. And then what you see here, 1/2, is of course that, because 2 plus h and 2 plus h appear on the top and bottom. Okay, but now we have the common denominator. All right, so let's go to the next page. The denominator h can actually be written separately if you would prefer. This is 2 times 2 plus h. And then what you see on the top here in the numerator of the numerator, it's 2 minus 2 plus h in parentheses, right? Don't forget that, because that's very important to have these parentheses, because that's one quantity. Okay, at this point, you can just take out the parentheses 2 minus 2. And of course, this negative sign gets distributed. It's negative h on the top. And this all over h. Now, because we don't like to really see a fraction inside of a fraction, you can also write this way. This is the numerator, okay? And the denominator is, of course, it's 1 minus, the denominator can be written separately as 1 over h. The denominator is h, but because it is the denominator, what you have here is the same thing as this, okay? The reason I write it this way is because now it's easy for you to see that h can be canceled, right? All right, so the difference quotient is going to be -1 over, should I just go ahead and write 2? Yeah, I don't have to really multiply this out. Okay, now, of course, you take the limit. And because I'm taking the limit, I'm not going to write the equal sign anymore. I'm going to draw this line. And you say, as h approaches 0, this approaches, and all you have to do is to substitute 0 for h. So you get 1 over 4, right? And that is the slope of the tangent line, which I described right here, right? And it does seem to be about 1/4, at this point. And so that is the correct value for the derivative of f at 2. Again, in a couple of weeks, if I ask you this, you would not have to go through all of these procedures because we will have some general rules to evaluate the derivative at any given point. Okay, so I hope this makes sense. All right, let's go on. Okay, so one last application and is from physics or from physical science. Let's say you're standing on a tall building here, 100 feet high, and you're going to drop this ball or whatever the object is. And if you assume that there is no air resistance, which is sort of ridiculous because that would never happen. But let's say you're in a vacuum or something, and you drop some object from the initial height of 100 feet. Okay, then we can describe the height at any given point t, as t is the number of seconds after you release the ball, is going to be 100 minus 16t squared. This is a well-known constant, 16, or actually 32 feet per second square is the force due to gravity. All right, so this is given. Now let's say find t s prime of 2. Now, what in the world are we looking for? Okay, this, as you know, is the velocity, or maybe I should say, yeah, the velocity of this object at time is 2 seconds. So after 2 seconds after the release, how fast is the ball going down? That's the question, right? So we could do that. It's going to look ugly because we don't have any nice general rules yet. And once you learn these rules, you will be able to just figure out the answer, probably without even having to work out this problem on a piece of paper. But at this point, again, all we have is the limit of the difference quotient. So let's go ahead and figure this out. Because we are looking for the time and the velocity at 2 seconds, this will be 2 plus h. We have to figure out what that is. And then we have to figure out what s of 2 is, and then divide this by h, right? And so again, this is a shorthand notation, so we don't have to write LIM as h approaches 0 every single time. This has two terms, 100 minus 16, and then t squared, so I would have to do 2 plus h squared, minus, and then this will be 100. Let's go ahead and put everything in the parentheses here. 100 minus 16 times 2 squared, right? Okay, let's erase this. All over h. It's a long fraction, right? But that's okay. This is 100 minus 16. And let's go ahead and multiply this out, square this. It's 4 plus 4h plus h squared. right? Remember the square of a plus b is a squared plus 2ab plus b squared. So you have this expression minus 100. And we can take out these parentheses by changing this negative to a plus. Plus 16 times 2 squared. Go ahead and write 64 because that's 16 times 4, which is 64, right? And then that is equal to, okay, again, the long h in the denominator, 100 minus, and I guess we can multiply this out, 64 minus 64h minus 16h squared minus 100 plus 64. Now I don't have to do a lot of arithmetic because a lot of these things will cancel out like this. Okay. Well, let's see. We can at this point factor out h from the numerator too, right? So you have negative 64 minus 16h. H cancels. Negative 64 minus 16h, and no equal sign here. As h approaches 0, this becomes negative 64. And so this is, let's see, what is that? It's feet per second. And so only after 2 seconds, the object is already going down at a quite a fast, quite a high rate or high velocity, which is negative 64. Negative meaning it's going down. Okay, 64 feet per second. And so this is an application. Now, do you have to do this every single time, right? And I have been saying no. And the answer is, of course, no, you don't have to do this kind of complicated process every single time, because we have, or someone has figured out much quicker ways of finding these for general functions. Okay, and so for the next few sections, what we will be learning is the set of, or family of, rules on how to take the derivative, how to find the derivatives of various functions. Okay, so we will start that in section 2, and this leads to the end of section 3.1.